So thank you for your presentation. Thank you for inviting me. And yes, I actually attended your defense. It was in my first year at Caltech. So I'm going to, it will not be so technical as Fernando did my presentation, because I am a master's in cybersecurity. I also did my PhD in cybersecurity, but I'm actually more now on the machine learning side. This is a brief outline of the talk. I will have much more slides, many more slides, but I will try to show a bit more some practical stuff. So this is what I'm going to go through. I will try to not sell my research, but actually show what I did, why I did it, and how it was done. And yeah, this will be more or less everything that we will cover. Like the first part is it will be I will show how I extracted the data, because machine learning is all about data. So I'm going to show to basically show how I extracted the data and how I used it later, and how we proposed a methodology as well. And basically, this is what I will cover, and then I provide the main takeaways of this presentation. So this is me. So I studied ICT engineering in now every university has this tech stuff. So I studied in Barcelona Tech, which is a technical university in Spain. Then I did the master's at Caltech. Then I also the PhD at Caltech. Meanwhile, I was for some time, for a few months, working in Malware as a machine learning engineer in the Android team. And now I'm currently a postdoctoral associate at New York University, Abu Dhabi, which I'm not actually much more involved in cybersecurity, but I'm still applying something, because my research currently is about privacy preserving machine learning for healthcare. So yeah, this is it, how it's now. And if you want to check my thesis, this is my thesis. So I'm just I know when someone writes a thesis, in the end, no one reads it much. So, but if you want to check it, it's here. It's 417 pages long. So, but I mean, it provides everything I'm going to show you here. So why my work was done? So basically, because there's still a high Android malware prevalence. There's a lot of actually, in 2018, when I started, it was seeming that it was a bit going down, but now it's racing up again. So as we can see, it's I mean, after Windows malware, then the next one is the next more targeted platform is Android devices. So it actually says here that 2022, the 1 out of 20 Android devices has malware, or can have malware. So this means that probably here there's quite many people with malware in their mobile phone, and actually don't know it, most probably. So that's why we have to create. Yes, sorry, because I'm going to, yeah, much better. Sorry, yes. So, and then also the main idea of why I applied AI is because we want to automate things. We don't want to, I mean, the work that Fernando does is amazing, but I mean, it's very complex. You need a lot of technical knowledge, how to reverse engineer. So with AI, what we are trying to do is to automate things that can actually be more automated. So we need data. We need data that can be easily retrieved, or at least not in a so complicated. So what we found when I started my research is that most of Android malware detection methods were what we consider static. So basically, people just create a model, they just run it, they test it, it says, oh, it has 95% accuracy, and that's all. So they don't think about that malware actually evolved, that how can this detection model, how can it be updated over time? As I say, this is back in 2018, 2019. Now it seems that it has improved a bit more. Also, all these studies, they actually use, or most of them are based on popular datasets. For example, Malgenome and Drebin, that date back to 2012. So malware in 2012 was much more different than what is nowadays. So it's actually not really meaningful that your solution works very well with these malware datasets, but you should show that it's actually working well with current malware. And they use emulated or real devices. Usually they never use both. And they assume that, I mean, the static features are always be the same because they are from the binary, but I mean, the behavioral features, like how like the application works on each one, it's assumed usually to be the same, and we were actually like thinking that it could not be the same. And this is why we started this also this research, like in cross-device detection. If we could actually like create a model on an emulated, getting information from an emulated device, that it could also detect malware run on a real device, and I will show something about this later. Also, it's very common in machine learning to randomly split the data. If we do this in malware, basically in cybersecurity or in Android malware detection, then this is a mistake. I mean, this is usually a mistake because then you this means that you are kind of like mixing. Usually, the training data, the data that you use to build your model, should be on the past of your future data. This is obvious, right? But when you randomly partition data, then you are mixing them up. So you are getting information to train the model that actually should be on the future, and so on. So this usually like this is historically incoherent, and it usually reports like biased results, like actually much better performance than it should be. And by then, and still nowadays, there was no publicly the dataset that included timestamps. Timestamps mean when the application was actually found for the first time, or when the application dated, or when the application was released. So we can actually do the first thing, I mean, correct the previous thing, which is like make them like historically coherent. So basically, we are building models with past data, and then we are evaluating with future data. So this all led to my data set, which is this here. I mean, it's not a perfect data set. It's actually not the data for the last 2 years. But what I try to do is to address like all these points here. So basically, try to address what is considered concept drift that I will show you. I will introduce later. But it's a publicly available dataset that actually uses timestamps, so people can evaluate the performance on future data, build models in a more like realistic way, let's say. So yeah, now let's go to the hands-on part. So machine learning models, or machine learning in general, it just needs data, lots of data. Usually more data, it's better. Especially deep learning models. I didn't use this because they were actually not needed. We found for many like cybersecurity problems, they are not so hard usually. So like traditional machine learning methods, they work well. We don't need so much data. My data set is not so large as I would, but I mean, it worked well with for our purpose. So how we can extract Android, how actually got Android data. So as I said, what we need, so it's like features. Features in a machine learning model is like attributes that make that sample like, let's say, not unique, but that for example, how could we define a car? Like an attribute could be the color of the car, and also it could be the size or the length of the car. And also how many, let's say, I don't know how many doors it has, like if it has back doors and all this kind of stuff. So this is actually like what we call features, and this is like the essential information that we use to build a machine learning model. To extract the features, what do we need? We need an Android rooted device. Why? Because we are trying to extract like the behavioral data. You actually need a root permission. So this is actually something that has to be done before. So this is, if you are doing this for Android for forensics purposes, then it's problematic because this can actually lead to you wipe all your data or it break the device. So in our case, we are always starting from an empty restored but rooted device, and then we need a bunch of tools. Here we didn't invent the tool. I just used like tools that they were available, like ADB, which is Android Debug Bridge, which is actually used to communicate with the device. Then some other tools that were used to extract static data. Then strace, which was used to extract system calls. There's a lot of information that you can extract at runtime, but we actually focused on system calls. And then some basic Linux commands, very basic, because I actually did most of my work with using a bash script, and a collection of APK files. So how did I do it? I did it this way. I mean, this is the workflow. It's not really important how it is done. I mean, this is how I did it because I had a purpose. So I started with the dynamic behavior because we actually wanted to have to build two data sets, one running on an emulated device and the other one running on a real device. So as I wanted to have for both devices, all static and dynamic data, it was important that the application could run on each device. So this means that the application had to be compatible with each architecture. So this was what it was the initial point. If the application was not compatible, then it was discarded, and we proceed to the next one. And then there come to two stages for static data collection, which is from the inside of the application, and then also using various total scanning service for different reasons I will show later. Then the data processing part, which is the most intensive for machine learning. It's to prepare the data to make it usable and feasible for a machine learning model to be used. And then this is how the data set was created. As I said, this is not the best. The way I'm going to show is probably not the best way. Probably nowadays there are much better tools, faster tools, more automated tools. But it was what was more or less available for me as a PhD student in 2018, 2019. It actually how most of the tools to do Android malware forensics and mobile phone forensics work, in the background. They of course don't say I'm using AAPT, but actually they are using it in the background. So what we need, as I said, the first one is to interact with the applications, and it's Android debug bridge. This is just it allows you using the command line. It allows you to interact with the phone. An USB cable, if it's a real device. In my case here now, I will show you with an emulator, but it will show what I'm going to show. It works in the same way with a real device. It had to be rooted. The advantage that we have here is I'm going to use an emulator, which is Genymotion, that it actually provides roots by default. So I'm skipping that part. And then you need developer options, which it can be done, obtained in this way. Well, you need enable first, under developer options, you have to enable USB debugging, otherwise you cannot connect with the phone. So wait a second, this is going to, okay. So this is the device, I have it here. That was, okay. So, I don't know why this is not working. Okay, 1 second. So, ADB, we press ADB devices and everything is, okay, we start well. Sorry. So if we press ADB devices, what it does is it actually shows this device. Here we see the IP of this the IP, which is also the same as this here on top. I don't know if you can see it here, but it's this number. I don't know if it will be seen anyway, because it's just yeah, I can tell. But anyway, just trust me. So this number here is the same as this number here. So this means that we are actually connected to this device. How do I know I'm connected to this device? Because I can basically do a lot of stuff. But let me see. Well, now I will have one problem. Okay. Anyway, so as this is the device that we have by default in Genymotion. What we can do here is the first thing I'm going to show is basically no, I'm not going to start with this. I'm going to start with the static analysis. So let's see we have a file, a sample. In this case, it will not be a malware sample because it's this is not a sandbox environment, so it was safer to not not use. So I'm going to use a test application. So if we run AAPT, which is this tool that it's like, actually, it comes from with the Android SDK. It's Android asset packaging tool, so it works to compile the binary, but also you can view, you can explore it, and you can extract information from it. So it's very easy to use, and if we run this, I mean, I used actually this command here because I was using Linux. But as I'm running here with a Windows computer, so I should use this command here. And then when I run this command, what it actually shows is, 1 second. For example, if I run this command, I mean, I have a test application here. In this case, this application is a legitimate application. I don't know if I can do this bigger, but is this cursor font? Maybe like this. Yeah, it's a bit better. So what we can see here is that it actually like goes through the binary, so to the like package application, and then it actually says like what are the permissions. Then you can extract this information and use it later to build a machine learning model. This is like one type. Permissions are really like is one of the features that are mostly used. Why? Because it's actually a security feature of Android. It has been improved over time. So nowadays they are quite restrictive, and actually the application it actually it's one of the security controls, or the first security control that Android provides. So it's a very useful one to discriminate malware from legitimate application. Because, I mean, if you are, for example, installing a calculator, let's say, but your calculator requires, let's say, to get your account information or to get, like, information from your contacts, this is not matching really much what should be the functionality. So it's actually something that it actually can give us a hint what's going on. This is one thing that we can use to build a machine learning model. And actually, I use this, and then I also started Intel filters, hardware and software features, the package name. We can also get the package name with here. Okay, if I put here package, we will see that the package name here is like, it says the package is com.chess. I chose chess because this is because it's like for the conference. But yeah, I mean, I could use any other. I was actually like, it was a bit tricky to find a good one. So this is the package name. The package name is how the application is known by the operating system. So it's kind of like unique. So this is how we can use it to name it. It will not be used by the machine learning model, but it can be used for us to know which application we are dealing with. And like this, we can extract a lot of information that is from the static point of view. Then the next thing I did as well, but this was like done in will be done in a different way, is to use okay, here is to use AndroGuard. What's AndroGuard? AndroGuard is a public tool. It was kind of back in time, it was kind of like not really well updated anymore, but I think that the developers went back. So now if you go to the GitHub, it's actually more updated than it was like a few years ago. So it's actually a very useful tool to go inside. I mean, to do the same stuff I did now with AAPT, but in a more like in a Pythonic way, because it's a Python script. So you can get much more information from the inside classes and methods and everything that is used. So what I did here is I used AndroGuard to extract the external API calls. The external API calls are API calls to the libraries, which means that they are not to internal or other internal methods, and they are sometimes used to characterize the behavior of the application. And how I did that? It was actually I built this script, very simple one, like it's the same as I did before, and then it just like you run it, and then we should get something like this. We get a list of what are all the like external API method that is called by this application. In this case, there are like almost 8,000 API calls. In this case, we are just getting that the API call is called at some point in the code, but we are not getting like the relationship between them. This could also be a feature that we could use, or how many times each one is called, and so on. But I mean, this is another feature that we used, and it can be used and extracted. And the last one I used for static analysis was VirusTotal. Nowadays, VirusTotal provides the version 3 of their API. But when I was using it back in 2018, there was a version 2. So this script is actually running version 2. But it's also very useful API that that allows you to have a report of the. I'm going to show you what is actually the example. I mean, to get a report of the application, what information can VirusTotal provide you? So it's in a JSON format. I mean, it's very small as well. So let me make it bigger. Something like this. So here there's also a lot of information that comes from VirusTotal that we can use. There's, for example, this timestamp here that we can use. This is the first time VirusTotal received this application. This can actually be relevant for us to date the application on time. How many times was submitted? I mean, a lot of information that is not really. It's much more like different. Also, this is like the number of files inside and everything. Yeah, the services that are running, the permissions here, they can also be extracted from here, and the detection report. I mean, it's a very complete, report, and basically, it's typically used to check if a malware sample is like, if an Android sample is malware or benign, because we actually want to be sure that what is malware and what is benign. Even though there's some studies that show that an application, it takes more than 1 year to stabilize the label. So not only if it's a malware or not, but also the malware family and all this relevant information about the sample. So it's it can give us a confirmation, but it should actually always be checked. Like the longer, the better, to confirm that something is malicious or it's legitimate. And then this was from the static point of view, and from the dynamic point of view. This is where like it comes the emulator here. So from the dynamic point of view, we can actually run. I'm now going to show to prove that this is working. Yeah, here I have this code. So how do I know that I'm connected with this? I mean, because if I run, let's see. I hope that it will work. If I run this here, the application should be installed. Sorry. Yeah. So the application is called Chess, as I said. So it's trying to install it. We are using ADB to install it. You see, like it appeared here. Like we have this Chess application here. Now I'm. So we are actually successfully connected to this. So we can use this command ADB also to do like many things. For example, like the thing I used it. You can also we can actually invoke a shell. So if we do, sorry. Now we have a shell in the device, so we can run, for example, like ls, and we will see the directory. Like it actually it's an emulator. So what we are doing here is like we have root permissions. So if I run who am I here, it should show that. But it's actually like we can use it to collect information. So what I did is like I used Monkey. Monkey is a tool that it can be used to from the command line to run an application. So now if it allows me to, yeah, sorry, I'm just properties. Okay. Okay, sorry. Sorry, 1 second. The thing is like this this keyboard is a bit, and the T is not working, so I should copy here. So I should copy it from here. Sorry? Control D. I don't think it's working. Yeah, thank you. So what I wanted to run, it was actually this. So we can use to programmatically run the application. Like I don't have to start it. I mean, we can use monkey, and then we can execute the command, the shell command, like in this way. So here we are using monkey. This one here is the number of events that we want to inject. So when we use one, it will just click on the. We just click the application, and it should pop it up. So if I do like this, let's see. Yeah, now it went up. So now it popped up the application. So it's just like if I put like kind of like 50 here, it would just like run just like some random like pressing, like it will simulate that some user is clicking on the screen. You see like this is like NB, I didn't put it. I mean, it's just like it's doing a bit of a mess, but I mean, this is like it's interacting. It's just like simulating like 1,000 random pseudo-random events. So it's just like if a user is just like clicking through the screen. This is, I didn't use it on my research because I was finding it like kind of like when random should, sorry, like the randomization is not, it might not be good because a user is usually not random. So what we wanted to do, we just use it on with one event. It was just to pop it up, and then what we were using is like we were using strays to collect the system calls. So with using this, we can, for example, like see. We can actually run strays like this way with this command line, and if we run it, let me see. I have to see if I can. So if I see, if I check which one is the the process is this one here. So it's 3090. So if I do this, I mean, of course, we will not do it like this when we run it programmatically. So we would do it in a way that there's no time. I mean, we just do it right after it. I don't know why this is not copy pasting. 1 second. Okay. Okay, it's 3910. So I'm using this to actually now I'm attaching strays to the application, and then we will be getting for 1 minute. This is like the 60, the timeout here. For 1 minute, we will be getting like the system calls that they are like released by the application. So this is a way like how we can get the dynamic behavior of the application. After 1 minute, it will be automatically detached, and it will, like, as I wrote this command, it will actually save a log file on this path, which could be retrieved, and it will be something like this. This will be what we will get. Like, so we will get like the timestamp, and also what system call, what's actually being invoked and what's being executed with the parameters and everything and everything that was used until during the 60 seconds. So this is something. This is some information that we can always use to basically characterize an application and then use this information to build a machine learning model. So this is the second. Yeah. So this is all the information I got. I mean, I ran it in different stages. So basically, all this was done because the final thing I wanted to do is to get something like this from an application. So I was having the various total report. I was also having like 1 second. Okay. I was also having the intents that the application was using, also the permissions that the application was requesting, also the system calls that they were using, and at some point I also, like, I did it later. For this is the name of the package name, but at some other point I also used the API calls, and this information was used to build machine learning models. This was all done before, like this was nothing new. So all this information was done by several studies before. But the thing is, like, there were like two main challenges that they were not used. They were not addressed, at least for mobile malware detection. In some other fields, this is very well known. I mean, there's one that's called like concept. I mean, this is like the combination of these three with the other ones, like concept shift, concept drift, dataset shift, dataset drift, like whatever, like distribution shift, distribution drift. Basically, what it means is like the statistical properties of the data, they change over time, meaning that your model that it was like built 1 year ago is not working anymore with the new data, because the new data is different. I mean, the new data, it cannot be modeled in the same way. So basically, if you keep the same model, it will fail. It will, at some point, it will not work anymore. So this was done. This has been known for machine learning practitioners for a long time, but somehow in the machine learning, in the Android malware detection community, it wasn't something that basically was ignored. So this is what actually we tried to address with our dataset, and also cross-behavioral consistency. This means that the behavior of an application, at least what we get from the system calls, that TXT file that I was showing you, like most of the studies like assume that it's the same. So it's like no matter what version, what Android version, what like operating system, what type of device, what architecture you run, like the behavior will be consistent. I mean, it's like a very bold assumption, and then also we tried to see if that was true or not. So for concept drift, there was some to address concept drift. There's one thing that is really important. It's like timestamps. To know if our model in the future will work, we should actually have like some data set or some way to order our data, so we can actually build data sets that are ordered chronologically. In that sense, like timestamps are very useful, or are like the key to address them, to order data sequentially, and we actually also like doing it in this way. We proved the existence of concept drift in Android malware detection, where like none study before had shown. But there are also problems as well, of course. First of all, like timestamps might not be reliable. Because there are many ways. There are many ways to data an application. One can be used like we can use maybe first seen from VirusTotal, which is when the application was received by VirusTotal. But this might be delayed because it can take time for people to update or to submit the application to VirusTotal. Another thing could be like go inside the application and get the last modification. So this means like what is the last modification timestamp that we can get from the application, and assume that that's the date of the application. So there are like many timestamps that we could use. we actually used these two that I said. I mean, they were not randomly explicit. I mean, yeah, and actually we proved concept drift in both cases. So as you can see here, we just like built two methods. Like basically, the summary here is like if the same model built initially, the initial model is in 2011. So if the same model built initially would perform well over time, there will be no drop. I mean, this is performance line, so basically the closer to the one, to the top level, would be the better. So if concept drift doesn't it will not appearing, then the line should be more or less like flat. We can see that it's going down, then up, then down, then up. This means that the model had to be updated, otherwise it will fail on detecting new malware over time. And based on that, like after proving that there was concept drift, like what timestamp should use? What's the most appropriate time, and what's the most feasible time? Feasible one. The most appropriate will be which one is the best to model concept drift, and if maybe it will be the same one that is most feasible. That means which one is easier to collect in a practical setting. So we started with these timestamps here, which is like 6. I will not go through them. They are like they are like explained and everything and much more thoroughly in this publication that we did a few years ago. But basically, we started with this, and then we showed, we performed a study like what are the most feasible ones, which ones are easier to collect, which ones are like more valid. It means that the timestamp is always in a real range, because actually a timestamp can be modified. For the last modification timestamp could be modified, could be put in the past, or could be put in the future. In the past, I mean 1980, where actually Android was not existing back then, or we can be 2130. In that case, the only reliable one is actually VirusTotal one, because VirusTotal is not, at least I don't know if they have some kind of like, they don't have any interest in modifying anything, they just like record when they actually submitted it. So in that sense, the first scene, which is called first scene by VirusTotal, but is when they were like received the application, is the most, let's say, reliable one in the sense of validity. But when we used it for other stuff, for accuracy, we just found that, let me see if I can see it. Like this is the first scene, so we see that it's not really accurate. I mean, it's always valid, but it's not really accurate, because 80%. How we did this here is like we have Android families here on the left, and then we have a time reference, which is where it says reference there. A time reference where the malware family is the first news, or if it's reported, someone reported about this family. Then we actually compared, like in our dataset, what was the timestamp based on first scene and all the other timestamps, and if it was actually on that close to this like first like detection or first like news time. And then we see that first scene here is always placing the applications later. So it somehow has a delay, which is logical, it's normal, because people take time. I mean, at least before, I don't think that this is not happening so much more now, but people was not really used to use VirusTotal. So it took time for people to submit the application for the first time. So this is like thing. And then we found that the last modification was actually more reliable, was actually pretty reliable on that, pretty accurate on that sense. So it could also, even though it last modification is in the scope of the attackers to be modified, it was actually not really modified. So then we actually end up with two: last modification and first scene. Last modification seems more accurate in general to locate an application, and first scene is more available, and it's more feasible, and it's more suitable. So we actually tried to see, like, okay, then which one do we use now? And then it was seeming like there was no solution until we did this. I mean, this is a very nice graph. I mean, I will try to provide the explanation for it. But it actually, here we use the last modification as a reference, and then we try to find for the difference between the last modification and first scene for every sample in our dataset. So we can see in samples that according to the last modification timestamp, the timestamp is in 2009. then first seen is very late. I mean, the gap is it's very long. There's even like 2,000 days, 3,000 days, which is this is the gap. So this is like according to the last modification timestamp, and this is the gap. So if you sum this time plus this, then this is the first seen timestamp. But the important thing is like it has been going down over time. So this means that the gap between both timestamps has been like going down, and this is until 2020. So this seems that for the last, at least like, I cannot say now, but I mean, we should continue studying this. But for the last, I mean, 2019, 2020, both timestamps are really like more or less locating applications in the same time frame. This is very good because this means that we can actually use first seen, which is valid. It's always valid, more feasible, more practical to collect, and also like it will be, it gets the attributes of being more of being accurate. So then we proposed a method which it was not really, I mean, it's not really our method, but we just like modified it and optimized it for the Android malware case. And the method is like, it's capable of detecting concept drift and adapt and basically keep the detection performance quite consistent over time. Here we are not doing anything. We're just relying on we are assuming that the Android data is a stream. So we are like we could be basically VirusTotal. We are getting the applications. We are like getting the information as I did before. We are getting the reports, the malware, and all that thing. And then what we are doing is like we are updating our model over time. So as time goes on, we are updating it with new information. We are predicting on new information, and we are using this new information to adapt over time. So it's a pretty complex structure here, but this is let's say an intelligent or a self-adapting model. And this is what we obtain. In the left is like with the last modification timestamp. In the right is with the first seen timestamp. So we see that the lines don't go back down so much anymore, and the detection performance is pretty consistent. Is the blue line. Then the gray lines is if we didn't use any our methodology. So if we use basically a one model and we don't address it. So we see that actually the detection performance goes down until basically here it's just like, it's worse than random. So it's just like, it's very bad at guessing what kind of like application we are dealing with, but here it's still like very good. Yeah, I'm going to pass this. And also we use this, that information before was for system calls. This is for permissions. So just using permissions, we could also like find if an application was malware or legitimate, just using permissions, and also using this self-adaptive method that we proposed. And the good thing is that we could also analyze what was like the most important features. These are the most important features over time to discriminate if an application is malware or not. I mean, these are permissions. This is the permission list. I mean, in the paper that we wrote about this, we go more thoroughly, like, but we can see that there are like some like clear patterns here. Like for example, here like this green appears to be much more important. I mean, it's not important before, and this blue also is very important during all this time frame, but it's not here, not so important after that. So there's like this is the method could also be used to explore concept drift on the to understand what's going on behind. And then for the cross-device detection issue, what we did is like, I mean, it was seeming pretty obvious for us, but I mean, there was no study before analyzing this. So we used a small data set. I'm finishing soon. We use a very small data set, but we use many platforms. So we use like 3 real devices, 3 and 6 emulated platforms. One's using ABD, which is the Google emulator, the official one, and then also using Genymotion. And then we just like run the same experiment and the same application like was run on the same device many times. And we saw is like, this is a comparison graph. I mean, it's quite complex to explain now in 1 minute. But the thing is, like, if it's actually true that that the behavior, at least from the system call side, is the same across platforms, everything should be kind of like greenish, and everything is white. So this means that the behavior is not similar. Or the only thing that is similar is on the real device side, but it's like on top of left up. We also ran this. We also confirmed this with with using machine learning models, and we see that the detection performance goes down in some cases, like, quite importantly. And yeah, just reaching the end. And the main takeaways is like we can use Malware forensics developer and also forensics tool to extract meaningful features to create machine learning models that also like self-evolve and self-adapt over time. This has an easy integration on pipelines, like like for companies and for the dynamic library features seem to be more robust, more but they are more time-consuming to get. And the concept-driven cross-device consistency should be considered in the design of any machine learning model, for Android malware detection over time. This seems something like really obvious, but you can see this is a paper that will be published in 2024. I mean, it has been accepted, and they still use Draven as one of the main sources of malware. So this means that we still have to work much more on the data that we use to build these models. And yeah, that's it. And yeah, this is my, if you want, we can connect, we can keep in contact, but thank you so much, and I hope that it was not really boring.
Thank you. We still have, okay, there's one question possible from the audience, if there is. If not, I will ask a question. Oh, okay. It's better to have the question from the audience. Oh, the microphone. Yes, please.
Okay, so I was curious, around the beginning, there was a graph describing, you were separating samples, APKs that were running on real devices and ones that were running in emulators, but if they didn't run in the emulator, they were discarded. How were they discarded? I mean, there's a chance that they are detecting the emulator, or that they are missing dependencies like Google Play services, or, for example, a specific service from Huawei, etc. So they are just discarded if they don't run, or do they take into account like if they are missing some dependencies, etc.?
Yeah, thank you. Yeah, this is very good question. So we were discarding them based on incompatibility. So if there was no, all the dependency, we just were installing it, or if it was needed. It's just like the architecture was not compatible. So if it was like, because all these emulators have like 64 bits, so it was mainly real device applications that they are for ARM architectures that were not running on the emulator. So that was the main source of being discarded. Thank you.
All right. Well, thank you. Thank Alejandro again.